Hi, everybody. We're going to get started at 5 minutes after the hour, which is 7 minutes from now. I will periodically repeat this until we get going. Feel free to comment. We can see all your comments on here, and we'll answer questions after a brief presentation. Again, we're going to get started in about 7 minutes. Thanks so much. Be cool to have some waiting music. We'll do that for next time. Going to get started at 7 minutes after the hour. Okay, we're going to get started in 6 minutes. Again, we're going to get started in 6 minutes. If you have questions, you can feel free to just drop them into the Facebook thread. Or you can also, I think, comment on YouTube as well. Going to get started in 6 minutes, which is 5 minutes after the hour. Getting it started in just a couple minutes. Okay, looks like we've actually got quite a few people here. So I think we should just start this up. So welcome, my name is Joshua Goldbard. I am the founder of MobileCoin. MobileCoin is a company that started, I guess it's about 2 years ago now, it was in 2018. And we're really excited to be able to bring this to you today. MobileCoin is a cryptocurrency that is designed for payments. It's designed for everyday use. We wanted it to be fast, simple, and just something that was a really easy payment experience. We think that this is something that the cryptocurrency and really the payments world at large wants. First and foremost, one of the values that we have as a company is just having the best privacy. And so we've worked very hard to be able to have that. Before we begin, I'd like to bring in Quinn DeVoe. Quinn is an artist from Palo Alto, California, who is going to sing a singer-songwriter, and he's going to be performing a song for us. Quinn, take it away. Thank you so much.
All right. Thanks for having me. Hey, right on, right on. Hey, right on, right on. I got your full moon fever. The night is young. I just wanna find me a lovely one. Hey, right on, right on. Hey, right on, right on. I got your full moon fever. The night is young. I just wanna find me a lovely one. Lord, the moon that never shines so bright. Everybody stepping out tonight. There's bound to be a real fine thing waiting for what I would bring. Lord, her lips are like a setting sun. Yeah, she letting me know the day is done. She bound to take me by my hand. Tell me that she understands. Hey, right on, right on. Hey, right on, right on. I got your full moon fever. The night is young. I just wanna find me a lovely one. Well, lost a lovely girl, I know you're there. Heart is desperately in need of care. Man, you
Great. Thank you so much, Quinn. We're super excited that you're able to join us today. We really appreciate the performance. Thank you.
Thanks for having me. Right on.
Have a good one.
Yeah.
Okay, maybe we can bring Matt Faulkner on. Wonderful. It's super wonderful to be able to support artists in the wake of COVID-19, and that's something that I really appreciate that we have the ability to do at MobileCoin, and it's a way that we can give back to our community. Speaking of community, Matt Faulkner is the first engineering hire at MobileCoin. He is the architect of our system and someone that I'm really pleased to be able to work with every day. Matt, if you can talk to us a little bit about what you're going to be speaking about today, and then maybe we could jump into the presentation.
Sure, absolutely. So today we're going to talk a bit about some of the privacy mechanisms that we've built into MobileCoin. And the overall theme here is defense in depth or privacy in depth. And so we're going to cover a number of different things, specifically about the transaction protocol and how our transactions are created and how they're processed inside of SGX enclaves.
Cool. Let's jump into the presentation. Take it away, Matt.
Sure, let's do it. So if you guys were to take a look at our GitHub repo right now, there's a description there that says MobileCoin is a privacy-preserving payments network designed for use on mobile devices. And that's accurate, but because this is a tech talk, we can go a little bit deeper into that. And so another way to look at this is MobileCoin is a quorum-based protocol for processing private transactions within Intel SGX enclaves. And that's all written entirely in Rust. So this slide is quite a lot to unpack all at once. And so really what this presentation is going to be about is the structure of the private transactions. And we're going to talk a little bit about how those get processed inside of Intel SGX enclave. So I mentioned that a big theme of MobileCoin is the concept of privacy in depth. And so we use a lot of different mechanisms that build up to a very private experience. And so to start this off, let's talk about some of the privacy mechanisms that we use to help ensure and protect the privacy of users when they receive MobileCoin. So if Alice, for example, was going to use MobileCoin, the first thing that she'd have to do is generate a pair of private keys inside of her wallet. And these keys are her private credentials for viewing her balance and spending MobileCoin. But these keys never leave her wallet and they never appear on the blockchain. Instead, when Alice wants to receive MobileCoin from someone, she generates a unique public address or sub-address that she can share here with Bob. And if she wanted to receive MobileCoin from someone else, like Carol, she could generate another distinct set of public addresses. In some cryptocurrencies, this kind of concept of having a sub-address is optional and recommended. But inside of MobileCoin, sub-addresses are the only way of sharing a public address. And we feel like this gives you the most amount of control about how you present your identity to different people. In this case, even though Alice is interacting with both Bob and Carol, just looking at the keys that she's provided them, they wouldn't necessarily be able to tell that they're both interacting with the same person. The next step is a technology from CryptoNote called one-time addresses. So if Bob is going to send some MobileCoin to Carol, instead of using the public address that she provided him with, he generates a new address denoted by this blue key, which is called a one-time address. And so what's interesting here is that this is the value that's going to appear as the address of the output on the blockchain. And you'll notice that it doesn't have anything to do, obviously, with Carol's public credentials or her private credentials. The next piece of this puzzle is that right now this output clearly shows that it's for one MobileCoin. And so the next piece of technology we use is something called confidential amounts. And here we've replaced the number 1 MOB with the MobileCoin icon, denoting that that number is now represented by a confidential amount. Under the hood, that's something called a Peterson commitment, but the main idea here is just to think that it's a confidential way of representing a value. So even though this particular coin or output doesn't have a lot of information in it that anyone could see, when Alice applies her own private credentials, she can see that this particular coin is addressed to her, and she can read the value that it's 1 MOB. Okay, so now Alice has some MobileCoin, and now she wants to send it. So let's talk about some of the privacy mechanisms that go into protecting her privacy when she creates a transaction. If Alice were just to say, I want to spend this one output, it might be pretty clear what's going on. It might be clear that she owns this particular thing, and it might be easy to analyze something in the blockchain where you can see that particular inputs were spent and sent to particular outputs. Historically, that's led to a variety of kinds of transaction graph analysis, where people are trying to figure out how a particular value flowed through the network. And so we'd really like to avoid the situation where it's very easy to figure out just what Alice is spending. So the idea here is something, again, from CryptoNote called ring signatures. And the idea is that instead of having just a single output that you're referring to, you would pull some other outputs from the ledger, which you might call mix-ins. And here we would group these together in what's called a ring. And when Alice signs that, she's saying, I own one of these. And so she can prove that fact without clearly indicating which individual coin she's spending. There's an extra detail to this, which is that if you're going to create something that lets you spend stuff without clearly indicating which one it is, you have to make sure that you can't spend the same coin twice. And so the way that that's implemented in ring signatures is by adding something called a key image, which you can kind of think of as a unique tag for everything that you spend. So if that key image has never appeared in the ledger before, it means that the coin being spent by this ring signature has never been spent before. Now, when we put that all into one transaction, what we see is that the transaction has some inputs and some outputs. Each input is spending a single coin and comes with a ring signature and a key image, and the transaction can contain multiple different input rings. The transaction can also have multiple outputs. We kind of went over that earlier, how these have a one-time key and a confidential amount concealing who the recipient is and the value of those outputs. The transaction also has a fee, which right now is just conveyed in plain text inside the transaction. And the transaction contains a few other things at the bottom, which we're going to get into a little bit next. So right now, this style of transaction might look pretty familiar from something like CryptoNote. And while that provides a lot of privacy, returning to the theme of privacy in depth, we wanted to make sure that these transactions are processed with the most privacy and security. And so they're actually processed only inside of SGX enclaves. And so SGX enclaves are a pretty big topic that we're only going to touch on a little bit, but you should think about it as having two really interesting properties. An SGX enclave is like a secure section of RAM within your system where you can run a piece of code so that the rest of the operating system and the kernel doesn't have visibility into what that code is doing. The second part is that someone can perform what's called remote attestation to convince themselves to get proof from the machine that that machine is running the correct code. And so together with these two things, you get confidence and confidentiality when you interact with an SGX enclave. In MobileCoin, when Alice wants to submit a transaction to the network, she submits it as an encrypted message into an SGX enclave within a node in the system. And so only the SGX enclaves can see the full contents of the transaction. If we were to voyage inside of the enclave itself would be able to see this entire transaction. And it would be able to perform the validation effectively in a black box. And so now we can kind of get into some of the extra things that are included inside of this transaction. The first thing that the enclave has to verify is that all of the input coins used in the ring signatures are actually real things in the ledger. So MobileCoin transactions contain a thing called membership proofs or Merkle proofs, which prove exactly that. And so the enclave can check, yes, everything that's claimed to be spent actually exists. The next thing it has to check is to say, well, I can't see the actual values of each of these coins, but I need to make sure that the amount of value going in is the amount of value going out. And so the first step in that is to do a little bit of checking around those values using a technology called bullet proofs or range proofs that ensures that all amounts denote valid amounts of MobileCoin. And the final thing that the enclave has to check is what's called a ring confidential transaction signature. And this signature does a number of things, but it primarily serves to show that everything being spent was actually owned by the signer and that the value of inputs equals the value of outputs. So that's the final check that the enclave has to perform. Now, there's a really interesting thing here. So now the enclave, which you've already established from remote attestation, is running the correct protocol code. That enclave has determined that this transaction is valid. It's safe to add to the blockchain. And so it turns out that we really don't need to keep around a lot of this information. We've already checked the inputs, we've already checked the proofs, we've already checked the signature. And so one of the things the enclave can do is it can remove that information in a process we call redacting the transaction. And the information that it needs to be able to publish outside of the enclave are the key images, which uniquely identify the coins that were spent by the transaction. And it needs to publish the outputs, or the coins that were created by this transaction. At this point, the enclave can also convert the fee into an output coin so that it has the same structure and appears identical to all other coins. Now, when the enclave is finished doing this, not just for one transaction, but all of the transactions processed in a block, it can emit these values. It can emit the total number of key images and the total set of outputs, and it can sign this block, indicating that it performed all of these checks correctly. And so one of the things that's really interesting about this is this block is quite small, and it doesn't contain the information that shows just which inputs were used in rings that created these particular outputs. And so by performing the validation inside of the enclave and then redacting that information, the block still has all the information we need to create and spend MobileCoin safely, but it doesn't leak any of the information that lets people do different kinds of chain analysis attacks. Looking at that, kind of stepping back at the whole blockchain, what we see is that the blockchain is just block after block of key images and outputs and the enclave signatures that show that these transactions were processed correctly. So just to kind of recap that, we're really shooting to have privacy in depth, and that means that we've used a number of different technologies to provide privacy to people when they receive or send MobileCoin. Several of these mechanisms originally came from CryptoNote, and so we did things like making subaddresses the default and only way of using public addresses. Output coins use one-time output keys so that individuals' identities are never directly written down onto the blockchain. We also use confidential amounts so that only the sender and the recipient ever know how much a particular coin or output is worth. And we use ring signatures, which provide privacy around which inputs a sender is sending. Now, these ring signatures and these rings are not normally visible on the blockchain, but in keeping with the concept of defense in depth, even if someone were to find an exploit around SGX and look into its black box, they still wouldn't be able to directly see which inputs are being spent. We had to do a few different things here to take advantage and design for use with Intel SGX enclaves. And so in particular, because we wanted to keep all of the information for transaction validation inside of the enclave, we included input proofs of membership for each member of the rings. And we added enclave signatures to blocks that indicate that the enclave correctly processed the transactions in a block. And just to recap that, it means that each block really only contains outputs and key images, and this makes the MobileCoin blockchain effectively immune to different kinds of chain analysis attacks. Maybe pause there and take some questions.
Yeah, cool. Thank you so much for that overview. I think that was like really, really effective and explained a lot of the way the MobileCoin works. I want to drill into the ring signatures a little bit.
Sure.
So just to be clear, essentially what we're doing with a ring signature is that there are, in this case, 4 different possible transactions that could be the one that Alice is trying to spend.
That's
and
right.
it's not at all clear from looking at that which one belongs to Alice. Is that right?
That's correct. This cartoon only shows 4. In practice, the current MobileCoin network uses rings of 11, but that's exactly right. Only Alice knows which one is being spent.
Right. So even if there were a vulnerability in SGX, there would be no way to tell really that any one of those transactions was more likely than the other.
That's exactly
Does that make sense?
Mm-hmm.
Cool. Great. So I think that what that establishes from my perspective is that in the presence of the enclave, there really isn't a transaction graph. And without the enclave, you still have this sort of like randomization of it could be any one of these different possibilities.
Mm-hmm.
And even taking that a step further, I think that you would need to have basically broken the enclave for all of time to sort of like have the full history of the different inputs. Because if you break the enclave only for, a week or a month, then you really only get the information for that month. And if the inputs in the transaction contain older transactions that are over a month old, then you don't really learn anything from the rings at all, right? Does that make sense?
Yeah. One of the kind of analogies I have in my mind for a lot of the chain analysis attacks is they're kind of like a gigantic Sudoku puzzle where you're sort of saying, well, I kind of think this one was spent here, so it probably wasn't spent there. And I think I know who owns this, and I think I know who owns that. And so you can do that kind of thing if you can see the entire history of the ledger. But like you were saying, if someone came up with an exploit that let them look into an SGX enclave, if they don't have all that history in the past, that's kind of like solving a Sudoku puzzle where most of the puzzle is actually missing. Like you don't get enough of the pieces of information to really easily conduct chain analysis attacks.
Yeah, so I think the really important way to summarize this is that if you had an SGX enclave break for the entire time that MobileCoin was operating, it's still as secure as any other crypto note-based currency. Is that correct?
Yeah, that's true.
Cool. And I think the ring CT stuff, the confidential transactions that are concealing the amounts, that really helps a lot too, because it allows you to not be able to correlate like this is from the set of like 5 coin transactions, this is from the set of like a half a coin transaction. All the transactions really look the same. Is that correct?
Yeah, so I think it's it's worth going back to this picture of the blockchain itself. And so when you look at that, you see key images, which they themselves have basically no discernible structure. There are 32 bytes that look quite random. And each of these outputs has a one-time key and a Peterson commitment or a confidential amount. And so everything in the ledger has the same structure. Another thing that's really interesting about this is that while these blocks look pretty small because they're cartoons, in practice, if you imagine that you had hundreds of transactions in a block, you may have several hundred outputs. And so in MobileCoin, the outputs are just sorted by their public one-time keys. And so if you had a transaction that maybe made 3 different outputs, like sending some money to someone, sending some money to someone else, and sending some as change to yourself, there's no linking of those particular outputs in the block. They just appear in the list of outputs wherever they would appear in the sorted order. And so the idea here is that every MobileCoin should be fungible. It should be equivalent and identical to every other one.
Yeah, I think that's a really important property of privacy is everything needs to look the same, because if you have some distinguishability of like this set of coins looks different than this other set of coins, then eventually you'll be able to do some form of statistical analysis. But if everything looks exactly the same, that's sort of like the basis of cryptography is, kind of trying to get everything to look sort of like noise. Yeah,
that's exactly right. There's been a fair amount of work looking at different kinds of, heuristics, for example, for looking at cryptonote ledgers, where they might find that, isn't it odd that these transactions are the only ones that have 1,000 outputs? And you start to say, yeah, that is kind of weird. Those must be all from the same process. They must all have the same meaning. And so getting rid of that kind of stuff and just making it so there is no difference, it's just outputs, really just stops things dead in their tracks when you try to apply those kind of heuristics.
Yeah. So just to summarize that whole point, in MobileCoin, there is no transaction graph. There are just outputs in the ledger, and they all look exactly the same. Cool. Can you talk a little bit more about the Merkle proofs and like why you had to build that?
Sure. So this was kind of an interesting puzzle. So when we go back to looking at validating and processing a transaction inside the enclave, we can say, like, what does this have to do? So first of all, when you send a transaction to the network saying, I want to spend some MobileCoin, you can't just make those numbers up out of thin air. You have to be spending things that actually exist in the ledger. There's a fixed amount of MobileCoin. It never grows or shrinks. And so every transaction takes in some MobileCoin and outputs some MobileCoin, and those two things have to be the same amount. So as far as the enclave is concerned, it has this transaction, and it needs to check that all of those things exist in the ledger. And so we kind of defeat the point of putting this transaction in the enclave if the enclave then turned around and asked the untrusted operating system, hey, do these particular outputs exist in the ledger? Then it would be revealing the members of these rings, and that's something that we wanted to avoid in the first place. So we needed to provide the enclave with a way of saying, yes, all of these things in fact do exist. And the way we did that is we kind of put the burden of proof on the person who created the transaction. And so when you're running a wallet and you're finding the outputs that belong to you, one of the things you do is you obtain proofs that each output exists in the ledger. And so this is kind of like using the core concept of a blockchain where you have all this data that's been hashed together. You can have a hash that says this is the state of the ledger. And so a Merkle tree is one way of saying here are a whole bunch of elements that all hash up to one single hash. And I can prove that one of these elements exists in the whole set. And so each of these membership proofs or Merkle proofs is a set of hashes that get you back to the root hash. And those prove that a particular element was in the blockchain. And so here, because the transaction creator added all of those proofs, the enclave can basically say, those all look good. And then it can just ask the untrusted system, is this the correct root hash? And so it's pretty much saying is this the state of the blockchain at some point in the past? And the untrusted system can say, yes, that is, that here's the hash that you should be validating against. And so the enclave gets all the information it needs to say, okay, this transaction is valid against this particular blockchain state.
So the thing that I really appreciate about this is that we did all this work to validate the transactions inside of the enclave. And then I think there was a day where we were looking at it, we're like, if the enclave goes and looks up which inputs belong to this transaction, then which inputs the enclave is asking for, right? There's no privacy or anonymity there at all.
Yeah, that's true.
And so we sort of had to invent this process where we're like, okay, what is an input? And an input is a proof that something existed in the ledger at a moment in time. And I think that the member proofs basically are a way of cryptographically proving that an input exists without actually looking up the input, which is super cool. Is that about right?
Yeah, that's totally right.
Cool. So I think that that's a very major difference in MobileCoin is that not only are these transactions validated inside of SGX, but there's no leakage of what things we're validating. When you are using an enclave, there's this concept of side channel attacks. And these are basically places where you leak information. Some of them occur at the hardware level when Intel has a bug, and other ones occur at the software level when the implementation has a bug. And so I think this is a really big thing that we ran into that was difficult. And our solution is actually quite elegant, at least from my perspective. And I'm really, really excited that we were able to do this because what it means is that when you suck a transaction or when an enclave is validating a transaction, it doesn't have to go and do a ledger lookup. It just says, hey, ledger, is this a state that existed at a moment in time? And that doesn't reveal which transaction you're validating within that state. Cool.
Yeah. It's also a great way of being able to summarize the state that the enclave was working with. And so that snapshot of ledger state is included in the enclave signature so that when someone wants to say, what was the enclave doing when it made this block, you can see that the correct piece of code processed the transactions against the correct ledger state. And so that kind of completes the trust story there.
Cool. Can you talk a little bit about how the actual amount concealment works? I always find this to be sort of magical where you are not able to, you don't actually reveal the amount of money that is on a check, but somehow you're able to verify that it exists within a range and the inputs and the outputs balance. That part is just amazing to me.
Yeah, so the confidential amounts are really cool. The piece of math involved there is called a Peterson commitment. And it's got a couple interesting properties. So it's basically, you can kind of think of it as the sum of two public keys. And so in this case, we're using, elliptic curve. So we have some kind of scalar times a base point. So you can just kind of think of it as being
what's a scalar?
A number, a big integer. And so
Cool.
you can kind of think about a Peterson commitment as saying, if I just said, here's my number, 5 times the base point, you'd just be able to look that up. It would be some big gnarly looking number, but you could just make a big table. You could say 1 times the base point is this point, 2 times the base point is this point. And so, you wouldn't gain a whole lot from it. And so Peterson commitment has just a really simple trick where it takes the value that you're trying to communicate and it multiplies it by 1 curve point. And then it adds in another value, which is a random blinding factor, or just a number that you came up with times a different base point. And because of the properties of elliptic curves, it's really hard to go backwards and say, what were the two numbers that went into that? So those are the secrets there. Like if you happen to know those two secret values, you can show them to someone and say, look, if you take these two things and you plug them into the formula for a Peterson commitment, you get this value that's on the blockchain. And so that's like, it's impossible to guess those things. And so being able to show those two says, I have the values that were committed to when someone created this. And so part of the way that this works is that when we create outputs, they have this one-time key. So there's some numbers there. And those do kind of an interesting thing where they can be used to communicate information to the receiver. It's sort of like a Diffie-Hellman key exchange. So the receiver can recover those numbers. The receiver can say, oh, I see the value and I see this blinding number that was added to the Peterson commitment. And so you can recover the actual values that go into that. There's some other cool stuff that goes into it. So for example, we want to make sure that when you make a Peterson commitment, the value is a valid number. So valid numbers here are 0 to 2 to the 64. And so there's some really cool machinery from the concept of bulletproofs. We're using the great implementation from Dalek about bulletproofs. And it's a zero knowledge proof that all of these commitments are in that range, 0 to 2 to the 64. That's a complicated piece of machinery, but really an interesting and powerful one. And then I guess maybe the last thing, we want to talk about how inputs equal the outputs. And so the kind of final really cool thing about Peterson commitments is they're additively homomorphic. So you can take a bunch of commitments and add and subtract them. And so you can basically say, if all of these things equal each other and I add them all together, all of their values on one side should equal all the values on the other. And so even though it's some kind of complicated machinery, it lets us express the ideas that, inputs minus outputs equals 0. And that intuition still works.
Yeah, so the way I think about this is that you walk to your bank and you get a check, or you do a withdrawal for $500, and then you basically want to give, I want to give Matt a check for $500. But what I want is when I'm going to the mailman, I don't want the mailman who's delivering the check to Matt to know that my withdrawal was 500 or that my check to Matt was 500. And so instead of writing 500 on the check, I just write down this mathematical formula, and I write the same thing on my withdrawal slip. And so by comparing the withdrawal slip and the check, you can see, if you're able to do the math, that both of those things balance without knowing exactly what number is being transacted. And so that's really cool. You can basically have what amounts to a transaction where the amount of the withdrawal and the amount of the new check that Matt can cash, those are equal, but nobody has any idea what they are.
Mm-hmm. Yeah, it's kind of crazy.
Cool. One of the questions that we have from the audience is, are algorithms being used to secure each transaction from quantum attacks? And I think that's kind of an interesting question. I think broadly the answer is no. Our algorithms are not quantum secure. Is that correct, Matt?
Yeah, I think we've been taking post-quantum cryptography to be out of scope at the present moment.
Yeah, so I think basically once we start seeing quantum attacks, or once the quantum proof algorithms are a little bit more proven out, we'll be happy to switch to them. It seemed like that would increase the complexity of our system, and it felt like there's still a lot of work that's being done in the quantum space. And so we wanted to be able to get to a sort of safer place before with the quantum proof algorithms before we started implementing them.
Yeah, that sounds about right.
Yeah. So the next question is, when can I send it on my mobile phone? And the answer is that we will be releasing an SDK at some point in the future that will allow you to integrate it into mobile apps. And then we are excited that people will take that technology and integrate it into their mobile applications. We don't have a specific date when you'll be able to send it on your mobile phone, but I would say it's coming. And I would say that once the SDK is out there, it'll be pretty fast to do it. This talk isn't covering the SDK, so I don't want to go too deep into that, but you'll be able to send it on your mobile phone. There was another question here about when will MobileCoin launch on exchanges? I just want to be really clear that we don't have any control over exchanges at all, and we have no idea when MobileCoin will list on the exchange, if ever. And so I just want to be really clear that what we're doing is trying to have the best cryptocurrency, and that's the project that we're working on, is just to make the best software. There's a question about what is the advantage of MobileCoin in practice over other crypto note-based cryptocurrencies. And I think the main advantage there is that there is no transaction graph, and so transaction analysis is not possible. There have been other cryptocurrencies that are based on crypto note where transaction graph analysis has leaked which transactions belong to whom. And so MobileCoin doesn't have that vulnerability. And I think that that's actually a really big difference. It makes it, I think, dramatically more private than other crypto note-based cryptocurrencies. But, everybody could actually take our technology and just implement it because it's open source. And we encourage people to do that because, that's the whole point of open source.
We can also mention, I think that we might have the edge in transaction speed at the moment as well.
Yeah. So transactions in the MobileCoin network, how fast do you think they go? What are we seeing right now on our test network, Matt?
I think I've generally been thinking about them as like around 5 seconds, but people have also been seeing things much faster. So, I'm always thinking about things from slightly a pessimistic angle. But I think we've seen a lot of transactions clearing in about a second.
Cool. There's a question about AML, and I just want to say that this conversation isn't about AML or KYC or any of that stuff. And so that's not something that we're going to cover today. If the audience has any other questions, I'm happy to answer anything else. But yeah, basically this conversation is intended to cover transactions in MobileCoin and how those remain private. We'll give it another minute for questions if anybody has anything, otherwise we'll shut this down.
If you haven't already taken a look at it, the source code is online. We've been running a testnet. We'd love any kind of feedback or participation, so give that a look.
Cool. And if you want to stay in touch with MobileCoin, community.mobilecoin.com is our forum. We're super active there. You can also hit us up on Twitter. Okay, Norbert has a question, which is, how scalable is it estimated to be at mainnet? How many transactions per second, roughly? I think that this is something that we're still testing because we haven't actually pushed the system that hard yet. Our intent is to be able to hold all of the payment volume that goes over the MobileCoin network. I think that if we do more than 10 transactions per second, we're one of the faster cryptocurrencies, and I think we'll certainly get there. I would be surprised if we did 100,000 transactions per second. So I think, we're going to fall somewhere in that range. I would say, I would hope that we could get to 1,000, but, that'll matter basically on how big the machines are, how many machines are in the network. It's fast enough that it's handled all of our testnet load without sweating right now. So I think that's the real point, is that right now we're able to handle our load. And at the point when we exceed the ability to handle our load because there's too much demand, we'll have to look at changing the system to make it faster. Does that about summarize it, Matt? Is that how you feel about it?
I think that's about great. So far, we haven't been trying to run on giant beefy machines or go too crazy optimizing things. So I feel like there's some pretty good room to grow.
Yeah, I mean, if we get to the point where there's 100,000 transactions per second of demand for the MobileCoin network, we could even go so far as to make custom hardware. That's definitely not what we're planning on doing right now. I think that if we got to 10 to 100 transactions of real transactions happening on the MobileCoin network, that would be a huge achievement in the world of cryptocurrency.
Yeah, that's totally true.
Zerk asks, will you be using the Stellar consensus algorithm? So Matt, maybe you want to talk about this. I know you've spent a lot of time on this.
Sure. So in the very beginning of this talk, we mentioned that it was a quorum-based protocol. And so we've done a lot of work reading through Stellar's consensus protocol, and we've cooked up something that's quite similar. So if you just wanted to have the one-word answer, it's yes, it looks a lot like Stellar's consensus protocol.
Yeah, so I think the key difference from my perspective is that we love Stellar. It's a fantastic protocol. We re-implemented Stellar in Rust. So it's a sort of like a clean room implementation of Stellar from scratch in the language Rust. And the other thing is that MobileCoin, the way that it works is that all the values that Stellar is consensing on are all encrypted. And so this isn't the talk about the consensus algorithm. We'll have a full talk about consensus because it's a huge topic. But the main thing is that censorship of transactions is extremely difficult in MobileCoin because the values that are being consensed on are all encrypted. Is that correct, Matt?
Yeah, that's correct.
Cool. Norbert asks, is it possible to bring the transaction time to under 1 second? I mean, theoretically, yes. I think that really is a question of load, how big the machines are, how fast the network links are. That's like mostly a system design question. Obviously, we want the transactions to be as fast as possible, but I think it's realistic for us to be able to say 5 seconds now. And if we can push it to under 1 second, we should do that. But I don't want to overcommit on the network until we've seen, live traffic hitting it. We'll have to go through a few Black Fridays and Singles Days before we actually know what the network's going to look like under load. Does that make sense? Is that correct, Matt?
Yeah, I mean, working remotely for the last several weeks, sometimes it takes 5 seconds to load the Google homepage on your home Wi-Fi. So, network is real.
Yeah, we're certainly not going to be running the MobileCoin network on our home Wi-Fi. I mean, I guess you could. It would be pretty difficult, though.
Yeah, that's true. That's fair.
Yeah. I think that nodes that do consensus will need to be internet-facing services that have, very large internet connections, big machines, because this is a performance network. We're trying to make a thing that handles a significant portion of world payment volume, and in order to do that, you really need an internet-grade service.
Mm-hmm.
Cool. I'm going to give it another 30 seconds for questions. Otherwise, we're going to close this down. Anybody got anything else? Couple more seconds. Yeah, let's go ahead and close it down. I really appreciate everybody coming out here. I really want to thank Quinn DeVoe for singing for us. We'll post his information on the YouTube and on the Facebook links. This has been really fun. If you have any questions, please go to community.mobilecoin.com. I want to thank Matt Faulkner for joining us and explaining all about transactions. We'll do deep dives on all the different topics on here in further tech talks. One thing that I want to say that's really important to me is that this is a team effort. MobileCoin would not be possible without all of the people who work at this company trying really hard to make something beautiful. We've been working for years to develop this software, and we're super excited for everybody in the world to see what we've done. If you'd like to try out the MobileCoin software, you can actually download a testnet client and send a transaction right now. You can do that by following the GitHub link that's on the screen. Thank you so much. Have a wonderful evening, and we look forward to future tech talks. Have a great night. Thank you.